All right, so we have made it to the last day of lecture. Woohoo! Mixed emotions, maybe. Mixed emotions. So here's what we're going to do today. Final review. Hopefully you guys got the Piazza post that said that the project has been extended for everybody till Friday. So if you're still struggling to get it done tonight, then you don't have to necessarily kill yourself over that. Please don't prioritize this over other things that are also important, right? I mean, I love that you love computer science and whatever, or maybe you hate it, whatever. But please, make sure that this, the extension doesn't screw up the rest of your other things. All right. So hopefully that'll alleviate a little bit of stress anyway. Let's see. So we have the final on Monday during class. Just come here. We'll do it. As I've said before, the final is going to be a little bit easier than the mid-year. At least I hope it will. I'll try to QC it a little better so that we don't have any crazy hard problems on there. What we're going to go over today is all the stuff that we've done since the mid-year. You are still allowed to use a back and front sheet of paper. You could use the original one you had if you can fit more stuff on it, but you can't bring both. Use the thing. Yes, Alexandra?
Can we pick up our...
Yeah, I've still got the old ones if you want to pick them up. Maybe I'll leave them in a box right outside the door or something. My door? Sure. Okay. The exams, you should have gotten a PDF online. Yeah. Email me if you haven't figured that out, you haven't gotten the exam. Sorry if you didn't know that. All right. So let's see. What else? So first things first, please don't forget to do the class evaluations. If you haven't, normally we try to do that the last day of lab, but since lab was a little weird this year and it wasn't even open then, it didn't. I couldn't let you guys do them then. So please try to remember to do that. Constructive feedback is always appreciated, and we try to get as many people to do the evaluations as we can, just so that we get the best spread of what people think about the class, right? If I forget to tell you, then a lot of people forget, and it's not giving you the voice that you should have. Okay? Here's what we're going to go through in the stuff today, all the stuff we've talked about before today, and then at the end, we're going to recap the results that we did on day one. So I'm sure you all remember exactly what we did the first day of class in January, before Snowmageddon or whatever it was. But we're going to review some of that, and you'll see that you guys have actually learned a lot this semester. Woohoo! Okay, so we'll see that. And then we'll talk a little bit about future data structures. And I actually, so crazy, this morning I was reading some articles online and found a quote that's exactly appropriate for this class from an odd place. So I'll show you that at the end. Okay? Any questions on Boggle, the final, anything else at this point? No? Okay. So let's review. Let's start with priority queues. Okay, I mean, I say up here that we're gonna have heaps, but really the abstract data type that we care about is this thing called the priority queue, right? And priority queues, the analogy I always use, or even the example that I always use, is that a priority queue is like an operating room at the hospital, right? I mean, the people that get served first at the operating room are the ones who are in most dire need of medical attention, right? And it's completely done on priority. So if you walk in there and you've sprained your ankle, you're probably not going to get helped for 4 hours, right? Because other people come in and they're bleeding profusely, and those people have a higher priority. So we have lots of examples of this in real life, and we can model that with a priority queue, which basically says we're going to be able to get the min element or the max element, depending on how you actually describe what your priorities are. A lot of times we'll pick min element because we say that number 1 is the highest priority, for instance. And then we also can insert, obviously, into this, and we can remove the minimum element, right? So there's actually, this is incorrect, isn't it? The min element for a heap is what? Yeah, constant behavior. I don't know why that's saying the wrong one. Constant behavior. Oops. Hang on. Whoa. There we go. Oh, 1. There we go. Sorry? Remove min is not order n, but we'll talk about that. Okay? So as far as how we originally thought of priority queues, we said, look, let's first model them using a regular old dynamic array, right? A dynamic array in an unordered list. And when you do them in an unordered list, number, 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 right? You've got this priority queue, and it's easy to insert into an unordered list. Where do you put it? At the back, right? You stick it right at the back, and all you have to do is update like 1 or 2 in one integer, basically, and you have constant behavior. You don't have to worry about all the other ones because it's an array. To find the minimum element, though, you have to actually search through the whole thing, right? And if you search through the whole thing, that's your linear behavior, right? And the same thing for remove. What do you have to do before you remove? Find it, right? And that's the same search. So if you have an unordered list, then the behaviors are OK. I mean, you get great insert behavior, but pretty terrible remove and min behavior. So not great. So we said, fine. Let's do it with an ordered list. And an ordered list, you keep everything in order. But the problem with that is, how long does it take to insert? Into an ordered list, you may have to look through all the items before you can get there, right? Before you figure out how to or where you're actually going to put the value. So you do have a trade-off here where you put it into an ordered list and it's linear behavior, but you get great behavior when you're trying to find it. If you have all your priorities in the list and the lowest or the highest priority is at the end, how hard is it to figure out where it is? It's always right at the end, right? Yeah, question. So no.
Isn't the ordered list kind of insert for that kind of dependent on how you decide to find your spot in the list? Because if it's a binary search, because if it's already ordered.
This is a good question. You know, it's too bad you asked that. Because I was going to ask you guys this on the final, but I guess I can't now. Good question. This is a good question, and it's probably better that I talk about it in class here. The question is, for those who didn't hear this, the question is, hey, wait a minute. If your list is already inserted, can't you just do a binary search to find the position and insert it right there? And you could do that, right? But let's talk through what the issue is here. So let's say you have an ordered list. Let's say that we order it reverse list. Why not? 20, and then 17, and then 4, and then 2. And we're going to insert, I don't know, 10. OK, so you're right. You can find that location almost instantly, right? You go to the middle and you find it. What do you still have to do? You still have to shift everything over, right? So you're still going to have to shift that and shift that. So you could put the 10 in there, but then you've got the 20 and the 17. And you have to first shift the 4 over and the 2 over. Or you first have to go backwards, shift the 2, then shift the 4. You actually don't get any benefit from that, right? So finding it isn't the hard part. It takes the same amount of time, but as long as you're finding it, if you shift while you're finding, it's the same idea, right? So doing a binary search is helpful in the sense that, sure, you can find it, but inserting doesn't help you at all, right? And now I have to come up with a harder question for the final, so sorry. A different question anyway. Although I didn't tell the other class, so maybe you guys could get the benefit from it. They can watch the video, yeah. Actually, it's funny, they can watch the video because the other video, I didn't have the camera working, so anyway. OK, so the ordered list, that's a trade-off. And then we have the heap. Now, we could use a binary search tree, and we could get good behavior on the binary search tree as well, right? Especially if you kept a pointer to the min element, you could at least get the min element more or less quickly anyway. I guess this beats it to some extent. But the other trade-offs for the binary search tree, it's a little harder to build a binary search tree. OK, and it's also a little hard, especially if you're going to keep it balanced. It's not so good. But a heap is the perfect data structure for a priority queue. OK, and we'll see on the next slide why, just so you can remember why. So a heap, remember, a heap says it has this situation where the node, whatever node you're at, all of the children of that node have to be a lower priority. OK, what do we call that idea that this heap has this property that all of the items that are lower in the or all the children are higher or lower priority? What do we call that idea? Yeah, an invariant, right? So this has gone through the whole class. We've had these invariants. The heap invariant is for your node, every child has to be higher or lower priority. OK? And you can have a min heap or a max heap, depending on how you do it. Most of the time, you'll see min heaps. Okay? And remember, min heaps have no ordering in here. The 10 and the 8 could be swapped, and as long as everything lower is still proper, in fact, it is in this case, the 10 and the 8 can be swapped, and it's still a heap. Okay? Because it still meets the heap property. Yeah?
10 and 8
Next.
would represent the priority of it.
Yeah, the 10 and the 8 represent the priority in this case. And in fact, we say that the 5 has a higher priority than the 10 and the 8. Perfect. Okay? So that's how the heaps are like they look, right? They're a tree structure, but they have this interesting invariant. Right? Remember, heaps are complete binary trees. In other words, they are trees whereby all the levels are filled in completely until possibly the last level, which can have empty ones, but all the empty ones have to come to the right of all the other ones. Okay? The reason we do this is because of the way we're storing it, and it makes it so that some of these operations, namely up heap and down heap, are very easy to do. Okay? So this is why you have to have this complete binary tree. How do we store these? We store them in an array. And remember, we put the root of the binary heap at position 1. Anyone remember why we do that? Winona?
So that when the math works, when you have children, so the children would see it like if it's multiplied by 2 plus 1 or multiplied by 2.
So, yeah, so that's why the math works. Well, we could make the math work if we didn't do it there, but the math is like slightly easier, right? The math is, you don't have to worry about a special case when you're figuring out the child or the parent. But the math that Winona's talking about is this idea that if you put these in an array, if you want to find the child of if you want to find, say, the left child, you just multiply by 2 of the index of the one you're at. So the index of 5 is 1, so you multiply that by 2, and the left child of 5 had better be 10, right? And the right child is just 2i plus 1, right, which is 3, so that's 8. Same thing for if you wanted the 8's right child. You would do 2 times index 3 plus 1, which would be 7, and 8's right child better be 13, which it is. Okay, so it works out very nicely in this array-based system. Okay? The other reason that we don't care about the initial one here is because generally for our array sizes, we do them in powers of 2. Right? So in this case, we do 2 raised to the 4th power. Right? That's how many elements we have in the array. But in a complete binary tree, there's always 2 to the n minus 1 total elements. So it just works out. The math works out that you've kind of always got 1 extra anyway, and it's just easier that way. Okay, so we put that. We can use that if we want to do swapping and whatever. But that's that. So that's what a heap actually looks like. Okay. Some of the heap problems we can do are the remove min, and we can do the add or insert, and we can also do find min. Remember that there are 2 functions we have to be able to do, right? We have to be able to take a node and down heap it, and we also have to be able to take a node and up heap it. Okay, so let's practice those in here. And if you're rusty on this, well, this is a good chance to become unrusty, right? So here's what I want you to do. With your neighbor or by yourself, start doing the remove min for this heap, and I will start writing it on the board. Okay?
Yeah, I just I'm just pushing 8 up and then 13. Oh yeah.
Josh? Correct. Yep, it's not a binary search tree. It's just a heap. If you forget how to do it, that's no worries. We'll do it in a sec. All right. Let's see if we can figure out. Hannah, do you remember how to start this? What do you do?
If I remember correctly, you basically swap 5 and 43.
in this case, we're just going to return 5 because we're not trying to do a heap sort. But you're right. So 5 is going to get returned. And then what do you, 5 is going to get returned. And then what are you going to do? Why 43? Yeah, it's the last one. So it's going to be the one that's going to replace the top one here. Because after we get this complete, and it's not yet, we want only those ones in there. And this is the one that needs to go away. So you're absolutely right. OK, now what do you guys think we do with this one? We down heap it. And down heaping is a simple matter of doing what? Finding which? Finding the next highest priority, or in this case, the lowest of the children. This was, I say it's easy. It's easy for us as humans to go, which one is it? It's going to be 8. Let's swap that one. Remember, it was a little tricky when you programmed it in lab, right? By the way, definitely go back and look at all your labs. And as I said before, if you haven't completed the labs, complete them, and I'll give you credit for them. You just have to email me and say, oh, I finished them. So we're going to swap the 43 with the 8. OK, 8 and 43. And then what are we going to do? Check again. 43 gets swapped with 13. And then what? We're done. And is it still a heap? Yep. Does it meet the heap invariant? Sure it does, right? And by the way, the 8 ended up at the top. And there's no other way it could have happened, right? The 8 had to end up at the top that way. OK, otherwise it could not have been a heap beforehand. OK, that's the bubble down or down heap. And notice we have a proper heap with the last one being gone. OK, so let's add 6 to this heap. Where does it need to go? Yeah. Question.
If you had 43 and 22 switched, and you had taken the last one, 22 ended up on the right.
Yep.
Then it wouldn't be a heap. Oh, wait, bigger. Sorry.
Yeah, it's the lower one's the heap in this case. Yeah, good. All right, you want to start us off on how to do add 6? Do you remember how to do that? OK. Somebody else. Fago, do you remember how to do it? No? Uh-oh. We got a little bit. Go ahead. Oh, Ben, you had your hand up. Why don't you just answer a minute ago? Ben.
You added to the last spot.
Yeah, is that what you're going to say, Winona? Yeah. You add it to where?
The last open element in the...
Well, yeah, the next open element, I would say, right? So it would be here. OK, so for you guys who are rusty on this, if you're adding one, you add it in the next place, because at the end, this is what the heap has to have this many elements in it. So you might as well add it where there's the next open spot. OK, we're going to walk us through the next part.
Then you go, like, if I divided by 2, so the parent is larger than the child.
Parent's larger, so what do?
You bubble up.
Bubble it up. And by the way, shouldn't the 6 end up as the root? Because it is the high. This is the person with the knife sticking out their neck if they go to the hospital, right? This person ends up going here. And it's a good thing computers are fast and that the staff at the hospital doesn't have to do this by hand, right? Right? 8's there, and then 12's there. And then what? And then you swap it again with the 10. You just check your parent, right? 6 and 10. And then what? 6 and 8. And the next person that gets helped is the 6, right? So that's how the priority, that's how you upheap on that. So upheap and downheap are both legitimate. I could ask you to code those. I think I'm probably not going to ask you to code the downheap because you did that in class. And remember, it took like 25 minutes, and it's a little hairy with all the kind of the special case of which one's actually smaller, does it exist, and all that. The other one's fair game. OK? All right. So let's see. I think we've got that. OK, any other questions on heaps? Yeah?
Was there a difference
Nave.
between bubbling up and upheaping?
No, bubbling up and upheaping are the same.
Okay.
Yep, they're the same. By the way, I could also ask you to do something, talk about how we do heapify. Remember how heapify works? If I give you an array, or I give you a bunch of items that are out of order, how do you make a heap with them? Do you remember how to do that? This is a good exercise to go through, too. Let's say that we had, I don't know, 5, 3, 2, 9, 6, and 7. OK? Let's put those into an array. First thing you do is you put them into an array. Right? We don't worry about the first one. 5 goes in there, then 3, then 2, then 9, then 6, then 7. OK? I'll actually draw this out in tree form as well. Right? It goes 5, and then 3, and then 2, and 9, and 6, and 7. Did I get them all? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yeah. OK. And then this. OK, so to heapify this, because this is certainly not a heap yet, is it? No, the 5's bigger than these ones, and it's not quite a heap. But what you do, if you recall, is you go to the first one that has children, which happens to always be the number in the heap size, divided by 2, floor function. 1, 2, 3, 4, 5, 6. So we're going to go to 3, which happens to be the first one that has children. 1, 2, 3. That one's the one that has children. So we start there, and what do we do with it? Do you remember? Bubble down, actually. OK? Do we need to do anything for the 2 and the 7 to bubble it down? No, because the 7's bigger already. Then we go to the next one backwards, and we do the same thing. Does 3 need to be bubbled down? No. It turns out I built this like almost a heap. OK, then we go to the 5. Does the 5 need to be bubbled down? Sure. Which one does it get replaced with? 2, like that. And we're all set. OK, and that will always work fine. OK, if you did all the bubbling down, you will always end up with a heap. And that's faster than insert, 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 insert. OK, it just happens to be faster. Question?
Is it going to be more about like writing up this function for this, or more about just explaining the process?
Could be both, writing the functions or explaining the process. Yeah. I'm not going to ask you one that's going to take like, I would never ask you like a really long recursive poem or something like that. Right? Never do that. Yeah, I'll try to make any coding examples be relatively small. OK? All right. That got more laughter than it should have, I think. All right. Question? Anybody else? No. OK. All right. So after we covered heaps, we covered sorting. And you guys got a little bit like really good at sorting. And who hasn't done their in-person sorting yet still? The in-person grading. Anybody? A couple people? You really need to either contact me or your TA. It's going to happen. It's scheduled, though? OK. If it hasn't, we do need to get that. And I'm going to send like an email to people who haven't gotten it done yet and say, please see me at some point, probably during reading period or something like that. But you got good at sorting, at least for 3 different types of sorts. And I hope that was a good exercise, like seeing the data for real. Like you finally got to see, hey, this is what an n-squared algorithm really looks like when you do the numbers, right? We had all these different sorts: insertion, sort, selection, heap, shell, merge, quicksort, radix sort. Here's what you need to know about those. You need to know that you need to be able to describe the algorithm. And I don't mean like shift the quicksort one to the left one and then I mean, you don't need to write that out. You may have to perform quicksort. Like I may ask you to perform quicksort on a list. But in general, it's I'll more or less ask you to either perform a few operations of it or just explain how it works. And what I mean for like quicksort is, quicksort, you pick a pivot, everything that's less than the pivot goes to the left, everything to the right of the pivot, everything bigger than the pivot goes to the right, recursively sort each individual list, right? That's about all the details I need to know, right? You should be able to talk about the asymptotic complexity and the best and worst cases for these. Don't worry so much about shell sort. That's a weird one anyway. But the other ones you definitely should be able to talk about. OK? Yeah, question, Greta. I mean, I could give you an array and say, I want you to do, here's the original array. In the next 6 arrays, quick sort it, or something like that. OK? So you've got to be able to, you've got to at least be able to show that you know how to do it for some of these. All right? Quick sort, let's see, what else? Some of the sorts are, most of the sorts are comparison sorts, where you're actually comparing 2 numbers together and swapping them or moving them somehow based on the magnitude of each relative to each other. Some sorts are not, like radix sort. Remember in radix sort, 2 numbers never got compared directly against each other. Right? It used some other property of the number. In that case, it used the property of the digit itself, right, to determine where it was going to go in this other queue. And then it ended up, after you ran the whole algorithm, they ended up sorted. Right? But you never did actual comparison sorts. For comparison sorts, the best you can do is n log n. Right? That's the best you could do. All right? Definably. When you get to comp 160, you will actually figure out why that's the case. You'll actually do that proof. You should be able to talk about sorts that divide and conquer can sort in n log n time. right? And by the way, what's the base of that logarithm normally? Base 2, because you're generally splitting it in half, and then half again, and then half again. And that's a logarithmic, base 2 logarithmic kind of operation. OK? So let's see. You also have to talk about like maybe sorting being in place, right? An in-place algorithm is the one where you have one array, and you're just moving things back and forth. Did anybody get a merge sort in place working? Did it work, actually? Yeah, tricky, though, right? Like lots of swapping, lots and lots of swapping back and forth, right? It's hard to do a merge sort in place, right? The out of place one, or the one that's not in place, is where you create new arrays and new arrays and new arrays and use those. Problem with that is you have more memory to use. So if you're running low on memory for whatever system you happen to be using, then an in-place sort might be necessary, even though it might not be the best one to do. All right. Other sorts have overhead that makes it so that it doesn't necessarily work great on small data sets. Quicksort's a good example. All that recursion and swapping and everything, not so good if you're only sorting 10 elements. Right? It just doesn't make sense to go through all the motions to do that. Easier just to use an insertion sort. It will be plenty fast. In fact, probably faster. OK? So that's the sorting type thing. So here's the kinds of things I could ask you. Like I said, describe quicksort. Right? Explain why divide and conquer algorithms lead to log n. Right? Divide, 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 divide. Kind of the binary search sort of method. You should be able to merge two already sorted arrays, merge them into one big array. If you know how to do merge sort, that's pretty straightforward, right? And this is what I was saying earlier. You should be able to perform an iteration or two of, or a few iterations of a particular sort. OK? To tell you how to do it. Yeah, Hannah.
Why do divide and conquer algorithms?
You tell me. If I'm taking a bunch of numbers and splitting it in half, right? I've decreased the problem size by half, right? And then I take that part and I break it in half, and the problem size is now half. If you do multiple divisions by 2, that's by definition logarithmic behavior, because for instance, if you have 16 items, you break it in 2, 2, 2, 2. By the time you get to 1, you've gone through 4 times, which is the log 2 of base 16, right? So that's how it works. Yeah. Yes.
For performing, is that like writing explicit code or like writing
No, I would say here's an array, and I'd give you the numbers, and then I'd give you boxes for the next part of it and say what happens in step 1, step 2, step 3. OK? Should be able to at least do that for most sorts. OK? All right. OK, so that's sorting. The next thing we did, and this was the big one, right? This was the one that we talked about for a couple days. Hashing, super duper important. Right? Hashing is super duper important because we've got this like holy grail of everything seems to be constant behavior, which is exactly what we want. Right? It's the reason that a lot of languages like Python and Ruby have like at their base level almost everything's a hash table because they're just super duper fast. Right? And they're useful for a lot of different situations. How does a hash table work? Well, you take a number that you want to hash, we call that the key, and you perform some mathematical operation, the hash function on it, and that gives you another number that you then use to stick into a table. Okay? And in that table, it's just an array, it tells you the place in the table to go look for it. Right? No need to look through all the elements to do it. Do you have a question, Max?
So whatever you're trying to store is accompanied by a key or whatever, or could be.
Whatever you're trying to store is accompanied by a key or is the key. The key and the data could be the same. Most of the time, they're not. Right? You're going to have some piece of data and then an associated key. Right? Right. OK? Or in many cases, too, the key could be, the data could be used as the key. Right? So even though it's not a number, let's say it's a string, there's string hash functions. We'll get a number out of a string. OK? So that's how you actually put it into the table itself. Looking it up, really easy. You apply that same mathematical function to the key again, and then you go to that place in the table and you say, is it there? Right? This actually works pretty well. OK, looks pretty well. Yeah?
Is that average case? And are you accounting for collisions?
Not accounting for collisions, but it is average case. It's what we call amortized constant behavior if your load factor is small enough, and you don't have repeats and things like that. So we'll talk about load factor in a couple slides, and we'll see how that works out. Okay, but it's constant behavior for all these different operations we want to do. Okay, all right. And like Winona said, you only get perfect behavior if there are no collisions, right, where two hash values go to the same one. And remember, you'll always have a collision, right? Anybody born on June 7th? Yeah, me too. Happy birthday in a month or so, right? There's a birthday collision, right? So we happen to have a birthday collision. And there was one in the other class too, right? So yeah, the odds are very good that you'll have collisions in a big amount of data. Now remember, it doesn't even have to be that big, right? Remember, I had that little Python program that showed for 1 million values, if you only put 2,000 things in there randomly, the odds are 95% of the time 2 of them will try to go into the same bucket, right? So the odds are very good you're going to have collisions. So you're going to have to utilize that, okay, and utilize the collision avoidance, or collision handling, I should say. So how do we handle collisions? Well, there's a number of different ways to do it. The first one was chaining, right? Chaining was one where we just say, if you have your array, let's say we have your array here and your table. What it means is if you're going to put a number in there, well, it's just going to be a little linked list going to number, depending on what the hash value is. You don't need to search for any other numbers in the table. You just go to that hash table, add it to the linked list, and you're done. Right? So that's pretty easy behavior. Right? No need to find a new bucket for a key. Don't even have to expand the table if you don't want to. If you don't expand the table, you'll probably run into other issues with load factors and things, which could get ugly, but you don't have to. Downside to this is that you have the chaining adds a whole new data structure. These linked lists, which we've already said are not that great in lots of ways. And if you don't watch out, you end up getting linked list behavior, which we already said was pretty terrible. So we go from this great data structure to this kind of terrible one if you don't watch out and you aren't careful. But that said, chaining's in general pretty good. So not a bad solution. Yeah.
So I talked to people at work about
Yeah.
tables that they've implemented, and they use chaining when they don't have insert strings or some type of data that is different than usual, and it's harder to know the easy copy constructor.
Oh, OK, so they use chaining when it's relatively easy to use data, like just integers and things like that?
They use
Strings or whatever?
they use chaining when it isn't.
When it isn't?
Yeah.
Oh, I see. They use chaining when it's not. OK. All right.
And they use
Not exactly sure why, but OK.
the linear probing when it is.
When it's harder to, or when it's easier
When it's
data?
easier.
Oh, OK. So there's different, depending on, and by the way, this is one of those things from this class, use the right tool for the job, right? So if you test, you might want to test both out and see what your performance is if you can write both of them, not too hard. OK, so that's chaining. The other one that we said was relatively easy to implement is linear probing. And linear probing is when you get a collision, right? Instead of, if you're supposed to go, let's say you have 7 in the hash table here, and if you try to put 6 in and it somehow hashes to the exact same place, then you just look to the next one and you say, is that empty? And if it's empty, you put it there. Finding it is the same way. You go to this spot and you say, is this the one I'm looking for? No. Is this the one I'm looking for? Yes. If you hit an empty, it means that it's not in the table. Josh.
Does this kind of essentially act in the same way as a linked list, though? Because you run your algorithm to find where you are, and then from there you just step forward to find what you want.
Yeah, I suppose it's similar in the sense that it acts in a similar way. But the big difference is no extra data structures. We need an array, and that's it, right? Don't need linked lists. It may behave in some ways similar, but the idea is that you don't have to allocate any other space and whatever, right? You'll fill up your table. Well, I suppose the load factor will still be an issue for you. Okay. What are the downsides to linear? The upsides to it are simple, right? It's pretty easy to go into your table, find the location, and then just keep walking around walking through the table until you find an empty spot. Easy. Downside, well, if you end up having hashes that group all together, then you might have to keep putting one in one spot and looking through this whole long list and looking through this whole long list. Okay, hopefully your hash functions better than that. But if that happens, you've got a bit of an issue. Okay? Yeah?
Removing another downside?
Removing is a downside, yeah. And why is that?
Because if you remove something to create and creates this extra space, now switching to your things.
Yeah, if you remove and there's an extra space there, you might miss some of the ones that come later. So what do you have to do instead? What do we do when we delete? Yeah. Mark it as mark it, and just say this one's deleted. Keep looking, right? And that adds its own downside to a little bit, but it works. It works in that case. Okay. All right. So that's that. To get around this grouping issue, we can do a quadratic probe. And a quadratic probe says, look, instead of adding 1, 2, 3, 4, we add 1 and then 4 and then 9 and then 16 and 25, because that means that we're doing it 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and you're just jumping farther along. Okay? It alleviates the problem of a whole bunch of hashes grouping up into one little location. Okay? Benefit, better for grouping. Downside, you definitely have to be a little more careful, right? Because sometimes you might have skips in the table where no matter what, nothing's going to end up in a spot. It probably doesn't happen that often, but it could. It could. Okay? All right. Another type, if you want to not go linearly or jump in this fashion, you can do what we call a double hash. Okay? Remember this doubles from the lab? This is the one where you say, I have a hash function. I'm now going to apply a completely different hash function if I get a collision. And that will jump it somewhere else in the table. And that location we'll use. And if we can't use that one because it's taken, we reapply this double hash again and again and again. So it actually just jumps it around the table more than either the linear or the quadratic. It's just another method. Okay? Again, you have to be a little careful when you're expanding, but it's not the end of the world. Yeah?
In terms of the double hash, like say you double hash it and then that spot is also taken,
Mm-hmm.
so in that case, would you have an entirely new hash or would you rehash it with the original function?
The way we did it in the lab, was we just kept hashing with the second hash function. That was all. Yeah, with an additional like jump factor. Remember? So the first time we did 1 plus or I guess we did, what was it? Was it 1 plus that one, then 2, then 3, then 4? I think we did that, or maybe it was times. I forget exactly. Yeah. A little bit. Does add a little more computation time, sure. But it spreads things out a little bit better. And if you have two good hash functions, you'll get fewer collisions overall. So, yeah. Yeah?
How do you do if your hash puts you to an array slot that is out of bounds?
What do you think? How do you put it out of bounds?
You have to expand.
No, you don't have to expand. You always do mod, right? You just say whatever your position is, mod the table size, capacity. Remember how we did that? We mod the capacity, and that will wrap it right around. 1, 2, 3, 4, 0, 1, 2, 3. If you do any number mod 3, it will always be either 0, 1, 2, or 3. Or rather, any number mod 4 will do 0, 1, 2, or 3. Yeah, good. OK. All right. So that's hashing. We had load factor calculations. The load factor is interesting. It's basically saying, hey, the number of things you're storing divided by the amount of space you have gives you some ratio. And you generally want to keep that somewhat small. It has to be less than 1, especially for the non-linked list tables. But generally, we try to keep it a little less than 0.7. This number is found empirically. In other words, for instance, the people who wrote the Java hash table function, they basically said, well, let's test out millions of things and see what works. What's fastest? And they say, yeah, 0.7 is pretty good. So it's empirical, right? Not really based on any other deep math. Okay. All right. How do you expand a hash table? Well, once the hash table gets bigger than your load factor, you say, whoa, I gotta expand this. You can't just copy the numbers or the locations because that will break your entire hash table. The hash values will not find your value again. What's that? Because the capacity changes and that mod factor changes. Yeah, that mod factor changes. OK. All right, so we have to do that. So what do? We just go through. So if you had a hash table here that you were expanding, let's say we had like this, 5, 7, 6. You would go to the first one, and you would then rehash it into the new table. Go to the second one, rehash it into the new table, et cetera. Does it take a little longer? Yeah. Does it amortize? Does it like make sense over the whole giant table? Sure. Not a huge deal to do it, but it's definitely more expensive than just copying. Okay, more expensive than copying. All right. Okay. What kinds of things could I? Oh, the other final one I forgot. We also did cryptographic hashing, right? We also did cryptographic hashing. By the way, how many people ended up going to the cryptographic lab the other day? A bunch of people. So was it interesting? Was it okay? All right. One thing that I talked about in there was part of the cryptographic hashing when you're, or the public and private key, when you have to do things like this. 1, 2, 3, 4 raised to the 1, 7, 9, 3, 8. Is that a big or a small number? It's a giant number. It's like 200,000 digits long, right? Turns out you then have to mod it by some modulus, right? I was having the program do this giant number through like this external program, and it took a while. Turns out, if you, who's taking Comp 61, discrete math? Did you guys talk about how to do this more efficiently in that class? Ah, you should have. It turns out you can do this much more efficiently by basically breaking this number into individual parts, and every single time modding it by that number, and it turns out it works great. So I rewrote the program, and it's now really fast. So I didn't put it back on the website yet, but I will do that. Yeah?
I just checked this. That number is 55,000 digits.
Yeah, this number, yeah, I'm sure this number is really big, right? 55,000 digits does not fit in an int. Let's put it that way. All right. So, but what you have to do is you can make this a much easier calculation, and it turns out it's not hard to do. OK, so cryptographic hashing was what? Cryptographic hashing was taking something, whether it's a string or a number or whatever, and applying a function that's a one-way function to this data such that you can't go backwards. At least you can't go backwards very easily, and in some cases you can't go backwards at all. But what it means is passwords and things now become secure because when you type in your password, it gets hashed into this other value, or this string, that is what you store when you check your password. And in order to check if you typed the right password in, you hash your whatever you typed in and compare it against the one that's stored, and that's how you do the passwords. Nobody who runs the tough servers knows your password. And in fact, they can't figure it out. It's impossible for them to figure it out because of the way that the system uses these hashes. Okay? You can use hashes for passwords, for digital signal or digital signatures, cryptographic hashes, electronic commerce. It all relies on this cryptographic hashing. That's what the lab was about a little bit. Okay? It's kind of cool stuff. Remember, there's basically 4 things for cryptographic hashing that we care about. You want it to be easy to calculate the value, right? You want it to be relatively fast to do these calculations, and it generally is. You want it to be infeasible to generate a message that has a given hash. Like if I give you a hash, you shouldn't be able to say, I can figure out what produces that hash. It should be almost impossible to do that. In fact, very, very hard. It also should be infeasible to modify a message without changing the hash. You don't want your message to say, bomb the enemy, or you don't want the message to say, don't bomb the enemy, and somebody changes it to say bomb the enemy, and you get the same hash out of it, right? Because the hash is what you pass to your comrades who do the bombing, right? So you don't want that. You don't want to be able to change the message so that it produces the same hash. That's bad news. You also don't want it to be able to find 2 different messages with the same hash. That's also related. You don't want hello to go to a hash and goodbye to go to the same hash, because that would mean that 2 things end up with the same hash, and you could use either hello or goodbye for your password. You really don't want that to be the case. Okay? So that's about all you need to know for hashing. Yeah?
Then why is it the case
Cryptographic
that
hashing.
in this regular hash, in just like when you're setting up a hash table, you're always bound to get collisions if there's a way to set it up so that the same...
Good question. You don't normally get collisions on this, or you don't often get collisions, mainly because we're not storing this in a table. So it's not like we have a fixed location. Instead of having like 1,000 places in the table, you basically have 4 billion places, and it's much more. You still get. It's not even billions. It's on the order of like quadrillions and things. Like you get like many more opportunities for a number. The number's huge, right? Versus you're not storing it in a table, so you don't need to worry about the space. Yeah, good question. Okay, that's hashing. Let's do a couple little practices on this hashing to get you guys remembering how it works. Here's what we're going to do. You're going to take the following hash function. It's really easy. It's x mod 9. Whatever the number is, mod 9, that's your hash function. Right? And you're going to hash the following keys: 5, 29, 20, 0, and 27, and 18. And you're going to do this twice. The first hash table is going to be with chaining. The second hash table is going to be with linear probing. OK? So try that right now. I will put it on the board, and I'll race you. OK? You can talk to your partner about it, too. Whoops. Done. Did I do it right? Did I make any mistakes? OK. Looks good. Who has questions about this? I know some people had some questions about it in the last class. Yeah?
Just in general for hashing,
Mm-hmm.
when we're implementing an actual hash data structure,
When we're implementing a hash data structure, yeah?
would we use like a function like a simple function like xmod 9, or we go online and find that?
Yeah, you use a better one. There's one in the hash lecture we did. We have a better one. It's like a plus b mod some big prime number, then mod the size of the table. That's a better hash function. This one was just easier to do on the board in 2 minutes. Right? But yeah, definitely use a bigger one. Other questions on how I did this? The linked list one's pretty easy, right? Just throw it in the right bucket in the linked list. And the probing one, you just have to find. Did anyone have any questions about how I got where 20 goes? Or not 20, 18? How did 18 get all the way over in 4 when it's supposed to be at 0? Everything was filled. It tried to go there, filled, 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 filled. Right? So it ends up way over there. So this is probably not the best table. By the way, what's the load factor of this table? 6 over 9, which is about 0.67, right? Should we expand it yet?
No.
Not quite. Maybe the next one, we'll expand it after the next one. Yeah?
So in terms of the linked list one with chaining, is there a benefit to inserting it at the front?
Oh, yeah. Well, yeah. For doing it on the board, there's a benefit because it's easier to write at the back. But you're right. Inserting it at the front gives you what kind of behavior in that linked list? Constant behavior in the linked list. So yeah, you'd probably insert it right at the beginning. Right? There's no point, unless you kept a tail pointer to your linked lists. Yeah, no real point. And no other real benefit to it. This ordering, who cares what the ordering is? Right? Yeah?
With the linear probing, if you had to expand it, and so you moved everything over,
Mm-hmm.
you'd start with that and go in that order.
Yeah, you generally go in this order. You know, it really doesn't matter. It actually doesn't matter. You can go in any order in here. You probably don't have the original order that you put it in, so you might as well go it in that order. Yeah, very good question. Yeah?
So the big difference between cryptographic hashing and this kind of hashing is that cryptographic hashing makes it really difficult to find out, and this makes it really easy to find.
That's not a bad way of putting it. I mean, cryptographic hashing has a slightly different purpose. Cryptographic hashing is saying, look, give me a giant number that came from this thing, and I can't figure out what the thing was. Right? That's kind of the idea of cryptographic hashing. You're not storing it in a hash table. Well, you could store it in a hash table, but you're not storing that as its key in the hash table. Like, that's not the point. The point is to have a unique number from this other data. That's kind of the point. Yeah, a hard to go backwards unique number. Yeah, good. OK, all right, so that's hashing. OK, one of the more important ones. You'll see this a ton of times in your later career. And you should, if you do like interviews for tech jobs, definitely try to know your hash tables pretty well. All right, then we've talked about graphs. OK, as I said before, graphs are the wild west of the node-based world. Right? They have no particular structure. They have no particular way of showing up on a screen. You could redraw this in a zillion different ways, right? Nodes do not have to have a particular number of adjacent, vertices. A vertex does not have to have a particular number of adjacent things. Could be any number. But in real life, this models a ton of different things, right? Google Maps totally uses graphs, right? Facebook totally uses graphs. All right, lots and lots of different ways of doing that. Computer networks, telephone networks, satellite networks, all these things are in the end case, they're really just graphs. So what are graphs? Well, they're node-based, right? We call the nodes vertices in this case, and a vertex generally has edges coming off of it. Okay, and this is an undirected graph because there's no arrows. So if two vertices have an edge between them and there's no arrow, they are both adjacent to each other. Okay? All right, what did we care about when we had graphs? Well, we cared about shortest path algorithms. Right? The shortest path between two places. Anybody have any friends in Comp 11? Yeah, they're all doing this right now, which is kind of crazy to me. Because it took us till the end of the end of data structure to get to this stuff, and now Comp 11's like, here's a shortest path problem, go. Right? So I'm like, a little bit intense. So I feel a little bit bad for them. What's that?
Are they being given the graph structure?
They're being given enough hints that they should be able to do it. They're given enough stuff, but they still have to comprehend this stuff, and so it's a little bit hard. Yeah, it's a little bit hard. So we had a couple different algorithms to actually figure out these shortest paths. First one was for an unweighted graph. In other words, no weights between the different between the vertices, right? Or the edges had no particular amount that we associated with them. The other one was for weighted graphs, and the one we talked about was Dijkstra's algorithm, which I'll remind you how to do. Okay? For the unweighted path, we'll go over this example in a minute. For the unweighted path, what we do is we pick a vertex, someone to start with, and we say, let's find the shortest path to all the other ones. You mark that one as 0 because it doesn't cost anything to get to itself. And then you look at adjacent vertices and you say, those are 1 away from me, right? Then you pick either one of those ones and you say, which ones does it, what are the distances to its adjacent vertices? Okay, and then you add 1 to that and you get the adjacent vertices. Okay, and then you just keep applying that until you have solved for all the different vertices and you've got the minimum distances. Okay. Question came up if I'm going to ask you to code this. If you want to learn how to code it, take Comp 11. All right? Still crazy to me they're doing that. All right. Here's the unweighted path one. Okay, you start with vertex 3. You say vertex 3 has 2 adjacent vertices, 1 and 6, and they are both 1 away. And then you pick either 1 and 6, and you say which ones are adjacent. Well, 1 has 2 and 4, so you just add 1, and you say now vertex 2 is going to be 2 away, and vertex 4 is going to be 2 away. And then 6 has no adjacent vertices, so it doesn't change anything. Okay? When you go to 2, let's say you did 2 next. Well, 2 is adjacent to 4 and 5. Well, if we went from 2 to 4 and added 1, it would be 3 to get to 4. But we already know that it's 2, so we're not going to change that one. We're not going to update that one. We are going to update the 5 to be 3. Okay? We're going to update the 5 to be 3 away. And when we do 4, it's going to be the same thing. We are going to update 4. is going to update 7 and update, well, it's not actually going to update 5, but it's also going to not update 6 because 6 is already 1 away. OK, so the algorithm is pretty straightforward in this case. Okay? This is called a breadth-first search. Breadth because it starts at one vertex and goes outward kind of at the same time. And this one goes outward like that. If it was depth first, it would be this one, then this one, then this one, then this, and keep going down one path. OK? You do need to know the difference between depth first and breadth first. Which type of container would you need to use for a depth first search? I'll give you 2 choices, a stack or a queue. Not a queue. It's a stack. For depth first search, remember you could do depth first search recursively? I don't know if you remember that from the maze lab. But you could do depth first search recursively, and that means you could use a stack to do it. Breadth first search, you have to use a queue for that. And I think I mentioned this in class that I had a former student come up to me 2 weeks ago and said, hey, I did a tech interview, and they asked me about breadth first searches. And I said, oh, I think I'd use a queue to do that. And they said, you're hired. Yeah, a little more subtle than that, but that's basically what happened, right? He nailed the interview because he knew about breadth first searches and have to use a queue for it. Okay? Level order traversal in trees is the way you use do a breadth first search for. Okay? So when we code this, right, we actually hold the data in a table. Okay? And that table is going to have a couple different things. It's going to have the vertex. It's going to have, and these are just arrays. It's going to, or some sort of dictionary or something like the map or something like that. And what we do is we have the known vertices and the distance to them all, right? And you start out and you say, look, the first one is 0 and everybody else is infinity. And you just keep populating that as you go through. Okay, just keep updating the table, and by the end you'll have the actual vertices. Generally, we'll also keep a previous column which says where you've been last, so that you know how to get back to, like, how you can actually find the shortest path. It really wouldn't be too great if Google Maps said, OK, to get to here from here to New York City, it's going to be 3 hours. Good luck. I mean, they don't tell you. They don't actually tell you the path. That's kind of a problem, right? So you need to keep the path itself. Question, Hannah?
Just clarifying, the D column kind of adds up as you go?
Yeah, that's the distance. That's the shortest path. So right now, before we've done anything, the shortest path is infinity for all of them because we have no idea. The shortest path for the first one is 0 because we know that it's going to be 0. You would start filling this in. The next thing in the table, if we went one more step, would be 1 and 6 would be 1 and 1 because it's 1 away from 0.
Right, and then the step after that, right? You update it if you know how long the total path is in each of those spots?
Yeah, that would be that. So far, that would be the total path. In fact, that would be the minimum because there's only one way to get there, really. So that would be the minimum.
Okay. And then in code, basically each of these columns is kept as parts in the node?
No, you would probably keep this in another table, separate table, like a struct of arrays or a struct of some other type that tells you the thing. Yeah, some other data structure. But yeah, but you keep that. OK, Dijkstra's algorithm, right? This was the one where it does the greedy algorithm. Right? It says, hey, what's the next best thing to do? Right? So Dijkstra's algorithm says, look, select a vertex and find the distance based on the weights of this, and then decide whether or not it's a good idea to use a weight based on which one we haven't solved yet that's the minimum. So it says, do all these ones. Which one of you guys is the minimum? I'm going to deal with you next. Which one of you guys is the minimum? I'm going to deal with you next. And that's how it does the search. OK? And it will always work that way. Let's go through the example. I think this is the same example we used in the actual slides. But here's how it works. You start out with a very similar table. OK? 0, we're going from vertex 1 now. OK, so it's 0 there. Everybody else is infinity. Vertex 1 is adjacent to 2 and 4. So if it's adjacent to 2 and 4, then you're going to update the table so that 2 gets a distance of 2, because it's 0 plus 2, and 4 gets a distance of 1. And then you will have completed vertex 1. OK? Which one do we pick next to go to? We have to pick, not 1, we did 1. We have to pick 4, right? We go to 4 because it's the minimum of the ones we've solved or haven't solved yet. 2 through 7 we haven't solved. The minimum one is 4. So we have to go to 4 next. And we check out 4, and we say 4 is adjacent to a whole bunch of things. It's adjacent to 3 and 6 and 7 and 5. So 3 is going to get updated to whatever 4 is currently, 1 plus 2 more. So 3 is going to get updated to 3. And you have to do the same thing for the other ones, right? So 3 gets updated to 3. And the other ones all get updated by adding the amount. So 6 would have gotten updated for 1, would have gotten updated to 9. Hopefully it did. It did. And you put where it came from, the last one that it came from. OK? That's how that works. All right. At this point, which is the next one we have to do? 2, because 2 is the next least one. Remember the table we did in class that one day on paper? I'm going to ask you the same sort of thing on the test. Right? So just remember how to do that. You should definitely study how to do that. OK? And then we have to do 2, and then 4 we do next, or 4 we don't actually update, because from 2, which is at 2 right now, if you add 3, it's going to be more than what 4 is already at. So you're not going to add any more to that. OK? And we keep going, and then we select either 3 or 5, because we could choose either one. They're both the same distance now, so it doesn't matter. And then we do that. We choose 7, let's say, and then we finally select 6. And once you do 6, which is not adjacent to everybody, you're done. How do you find the path, let's say, from 1 to 6? How do you find the shortest path? If I want to go to vertex 6, how do I find how do I get there? Using the table up here. Yeah?
Go backwards kind of. So
OK.
find which one it came
So which one goes to vertex 6?
from.
V7 does. And then
V7 comes from
V7 comes from V4. And then V4 comes from V1. And the shortest path is 1, 4, 7, 6 for a distance of 6. OK? So once you do it, you've got all the data you need. Right? And you can print it out like this. It's a pretty easy recursive algorithm. It just says, look, for each path, if it's not a vertex, you print the path to it, basically. OK? And that's it. Pretty simple. What kinds of things could I ask you to do? I could ask you to complete an adjacency matrix or an adjacency list. Remember, an adjacency list is saying, here's a vertex. What are all the things that are adjacent to it? Easy. Matrix is the two-dimensional one, which you have to figure out as well. You should be able to take a graph and tell me a breadth first or a depth first traversal. OK, we practiced that in lab. Should be able to find the shortest path either for unweighted or using Dijkstra's algorithm. OK? Ask your Comp 11 friends if you have trouble. OK? All right. The last things that we did was skip lists and Bloom filters. All you really need to know for skip lists is, hey, how do I create a skip list using the coin flip method? Right? We did that in class. We practiced it. Right? And describe like a property that makes a good skip list. What property makes a good skip list? For a level, where do you want? If you live in New York City, did New York City make a good skip list for their train system? Well, why not?
The values that get put on the express are not evenly spaced.
Exactly. The values aren't necessarily evenly spaced. Now, for New York City, it might make sense. But for a generic skip list, it's not going to make sense. You want them to be nice and evenly spaced. Okay? For Bloom filters was this really wacky data structure that you could ask it, hey, do you have a certain value? And it could say, probably, right? And it gives you a nice like random probability of being correct. You can't rely on that. But what's nice is if it says, no, I don't have that, and you can rely on that. And there are examples of when you might want to do that. Okay, a good one that we used in class was for the Google Chrome setup where it says, hey, are you going to a malicious site or not? Right? It'll look in the skip list, and if it says, is this a malicious site? And it says, probably, then it'll go to look at another list that it actually has in its server. If it says no, it'll say, oh, fine, this isn't a malicious site, and it'll go straight to it. OK, because it knows that it's not. All right? You should look up Bloom filters in email. Your junk filter might use a Bloom filter to actually figure out if it's junk or not. It actually uses that as well. So take a look at that. Yeah?
Is there like a converse
Richard.
of Bloom filters that give you like false negatives, but the
Yeah.
more give you false positives?
I don't know of one that gives you false negatives. I don't know of an anti-Bloom filter.
Okay.
Yeah, I don't know of one. There might be, but I don't know of one. If you design one, maybe you'll get a award out of it or something. All right. OK, so those are the data structure. That's pretty much what we covered since the mid-year. OK, that's what we covered since the mid-year. What I want to do now for a few minutes is go back and remind you of what we talked about way back in January, right? Which seems like so far away right now, right? What we did on the first day, you might not even remember this, but I'll refresh your memory. We took a bunch of containers, some of which you'd never heard of, right? I said, oh, we're going to do this thing with a hash table. And you're like, whoa, what? Well, guess what? You guys know about those now, right? And a binary search tree and a linked list and a dynamic array. And what we did was we threw a bunch of numbers in there. We tested them. We said, what is the timing for them, right? For these containers, we performed the following tasks, OK? We added 100,000 elements. And by the way, from your grading, you should know that you should be able to recognize that some things for 100,000 elements take a while, right? Your selection sorts took roughly 28 to 30 seconds in many cases. Selection sort, it's because it's a terrible sorting algorithm, right? And so to do 100,000 things, you're like taxing the computer a bit, 30 seconds worth, right? For other things, it doesn't take that long. So you can see that 100,000 does mean something to a computer generally. So we're putting the even integers in there, 0, 2, 4, 6, 8, etc. OK? Then we're searching for 50,000 of them. And we're saying, look, is 0 there? Is 1 there? Is 2 there? For the 0, it's going to say yes. For 1, it's going to say no. For all the odd ones, it's going to say no, it's not there. So however your search is happening, it's going to have to figure out if the ones that aren't there aren't. And it might take some time. Then we do 20,000 deletes. OK? For the numbers 1 to 20,000, same idea. We do 1, we delete 1, it's going to get deleted. We delete 2, but it's not going to get deleted because it's not even in there. 3, etc. OK, remember how we did that? Maybe you don't, but that's what we did. Here's the results. You do remember these numbers, right? Exactly. Take a look at what happened here, right? Remember on day 1 I said, I'm going to tell you the whole class that I hate linked lists? Well, this is why, right? Because the behavior's pretty crappy, right? Arrays, all not too bad, but not great. Hash tables are amazing, and you guys now know why they're amazing, right? Which is kind of cool. Like you learned enough to say, hey, this really, I know why. We'll talk about that more about that in a second. Binary search trees, again, you'll know why it's pretty good, but not as good as a hash table. And then the sorted arrays, better than the overall array, but still not so great. Okay? Yeah. Alex.
Are there any numbers for a try for comparison to the hash table? Or?
I did not do a try one. No, maybe I should. Yeah, you can always do the test if you want. Yeah. Okay. Although it's not going to be numbers now. You're going to have to figure out how to do strings. So doing a hash table with numbers would be weird. But could, but it'd be a little weird. So let's walk through these a little bit. Look at insert. Why is array inserting really, really fast? It's at the end. You stick it at the end. You're done. What kind of behavior is that? For each one, it's constant. For all n, yes, it's n behavior. But for 1, it's constant, right? Which is, now you know that. But what about searching through an unordered list, an unordered array? What do you have to do? It's linear. You have to search through all of them, right? And in fact, for each one, it's linear. So for the total, it's n squared, in fact, right? OK. How about deleting? Deleting does what? Has to find it first, right? And remember, we're only deleting 20,000. We're not deleting all 50,000. So that's why this number is less than the third search. But you have to find it first, right? Maybe I should have done 50,000 for that, too. Linked list, inserting's great. Where do you insert in a linked list? Right at the front. Constant behavior. Change 2 pointers, you're done. Right? Hash tables. Constant behavior for that, right? Also constant behavior for searches. Also constant behavior for deletes, because you find it first and then delete it. Right? Constant, constant, constant. Woohoo, we love it, right? Binary search tree. Pretty good to insert into a binary search tree, but this happens to be a balanced tree, so there's a little bit more overhead there, right? Searching really fast because it's what? Logarithmic, right? And deleting, same idea, it's really fast. How about the sorted array? Why is it so freaking slow to insert? You have to keep it, you have to do an insertion sort, basically, right? You can't just keep, so you have to take all that time up front to stick the numbers in. But searches, beautiful, right? Again, you're going to get behavior that's logarithmic, right? Notice those numbers are pretty close to each other, logarithmic. And then the deletes, same idea. You do have to move a bunch of things to delete it. So it's not the best, but it's okay. Okay. So do you see how that that actually, like, you guys can describe this table in pretty good depth, right? What I did was I ended up making 1 million. Right, so let's just try it on 1 million. Take a look at some of this data. Whew. I told my computer, I said, do this same thing for a linked list. And I came back an hour and 15 minutes later, and it was like, here you go. Right? Like, that's how long it took. Right? It took over an hour to do that. The computer just sat there and cranked away, right? Like, I could hear coal plants like firing up in the background because this thing was like doing it, right? All right? So it was like not so great in that sense, right? Not so great. All right? But what's interesting is, so this data behaves what? But here's the most interesting part. Especially if you've done your sorting grading, you'll see why this is so interesting. I just compared them to each other. The array versus for 100,000 versus 1 million. What do you notice about those two? It's about 100 times bigger, right? For every element, it's linear behavior for most of the stuff. So what does that mean for the overall behavior? N squared. Ah, terrible. For linked lists, notice this is over N squared behavior. Like, it's just terrible behavior, right? It started out 23 seconds, and now it's an hour and 15 minutes, or whatever, right? Hash tables, 0.2 seconds to do this. Hash tables, like, no problem, right? I like hit return, and it was like, I'm done, right? That was it, right? Notice it's about 10 times slower, because for every element, it's constant behavior. For 10 times as much elements, 10 times as much time. Oh, that's beautiful. Beautiful, right? Also, binary search tree, not so bad. Still took less than a second to do all that, right? Because binary search tree's logarithmic behavior is great. Sorted arrays, not so great, because you still had to add all those things in it. It took forever. Yeah?
If hash table is sorted behavior, shouldn't it still be roughly 0.018? Because
you're now doing 10 times as much work,
okay, yeah.
right? So you do have to do 10 times as much stuff.
Okay.
And so that's why it takes 10 times as much time.
Okay.
Yeah, but the data turned out great in this. Yeah, Nathan.
Could you speed up the sorting array by dumping everything into the array and then sorting it, as opposed to doing an insertion sorting?
Could you dump it all into the array and then sort it? Yeah, you probably could. You could probably do a different type of sort on it. Yep, absolutely. Yeah, you could do that. But if you need to do it as you go, you're going to have to keep it sorted. So that's that. OK, so that's the data. Same thing for the inserts. You could analyze this data. If I gave these two tables to you on the test, you could probably analyze them, right? OK, same sort of thing for the search. OK, now, in today's news, I found this, right? You guys remember that I said one of my favorite cities is Singapore? Are my Singapore people here? Anybody from Singapore in here? Yeah, a couple people, right? There's like 4 or 5 total of people in Singapore in the class, which is kind of cool. I love Singapore. In today's news, look at what the Prime Minister of Singapore said. I will condense this for you. He basically said, hey, I hired a really smart dude who knew how to computer program because I know he knows how to solve problems. And I hired him to be my Minister for the Environment and Water Resources. Why? Because he's a smart dude, because he's a tinkerer. And he builds apps, and he what does it say? He says he dabbles in robots and things, and he's like a smart dude. And then, this is the most amazing thing, the Prime Minister of Singapore said, the last program I wrote was a Sudoku solver in C++. Right? Now, why do I bring this up, right? This guy's not a computer scientist, but he took a class like data structures or Comp 11 or whatever, and he's now the prime minister of like a really important city-state in the tropics, right? So the idea is that hopefully, even if you're not going to be a computer scientist, and many of you won't, many of you will, but many of you won't, even if you're not going to be a computer scientist, hopefully this class taught you some like ideas that later in life you'll be able to say, hey, you know what? At least I learned something about solving problems or about like utilizing things. And so when you're the prime minister of some like tropical city-state somewhere, right? You can actually like end up with this sort of thing. Okay? So, and that was so cool that it was in today's news. Guys, there are thousands of other data structures out there, right? You think you learned all about data structures. What you did learn was not necessarily what the heck a spaghetti stack is. I have no idea what a spaghetti stack is, right? But I bet it's based on a stack in some sense. You guys have the base level knowledge for these data structures to be able to go and choose good data structures in your own code and your own programming. And hopefully after this class, you'll be able to go and look one of these up and say, OK, I can figure out how this works. Right? Or you'll be able to say, I'm going to program something, and I'm going to use the most efficient data structure. I'm going to do testing comparisons and so forth. OK? So I hopefully that's the takeaway from this class. OK? Now listen, you guys are awesome. Thank you for working so hard on your Boggle and for the other class. And if you didn't work hard and got away with it, good job on that too. I very much appreciate you guys being in class this semester and doing so well. OK? Thank you very much. All right? Thanks. Oh, thanks. Thanks. All right. If there's no other questions, I will see you guys on Monday or around the lab. OK? Take care.